Okay. Now we're going to talk about inclusion-exclusion for arbitrarily many events. So we've already seen inclusion-exclusion in the case of two events, right? That was the probability of A union B equals probability of A plus probability of B minus probability of A intersect B. For arbitrary events, so let's recall that for a second. The two events A and B, we have probability A union B equals probability of A plus probability of B minus probability of A intersect B. How about for three events? So we have three events, A, B, and C. And the assumption is that there's going to be some overlap among the events. There doesn't have to be. This will work in general, but part of the point is that there might be overlap, and we have to account for that overlap. Okay? So, let's call this A, let's call this B, and let's call this C. So what is the probability of A union B union C? So the way we want to start is we want to start out by saying, all right, let's count the probabilities of each individual event. So let's add them up. And what we're going to do is we're going to go into this Venn diagram and we're going to put a plus in each of the pieces. Hold on, let me modify this because it's going to cause a problem. Yeah. Let's have a little bit more overlap here. That'll make it better. But now I've messed this up. All right. So there's going to be pluses in all of these different sections. Okay, because that gets a plus for every instance of A, B, or C. Okay. I'm sorry. For A, we get a plus in these sections. For B, we get a plus in these sections. For C, we get a plus in these sections. Okay, so point is we've actually obviously overcounted. We've triple counted, double and triple counted certain parts. So now we have to get rid of certain pieces. Let's get rid of the ones where there's overlap between any two. Okay, so let's subtract off probability of A intersect B, probability of A intersect C, and probability of B intersect C. So what happens now is A intersect B is here and here. A intersect C is here and here. B intersect C is here and here. So what we have now is we need exactly one plus in each section. So right now we're okay here. Okay, we're okay here. We're okay here. We're okay here. Because those are only ever going to get counted once. And now after the second round, there's in this section, there are two pluses, one minus, that nets out to one plus. Two pluses and one minus, that nets out to one plus. Two plus and one minus. So now we have three pluses and three minuses, so we have to add back the overlap A intersect B intersects C. For one more plus in here, and now we've got it. Okay, so that's inclusion exclusion for three events. Okay. In general, how do we do this in general? Okay. So in general, how do we get probability A1 union A2 union A? All right, well, let's write down the formula. The way it works is probability of the union from I equals 1 to little n of AI is the sum from j equals 1 to n of all subsets of indices. So capital J subset of indices such that size of capital J is little j of the intersection of I and j of AI. But we have to take into account -1 to the power j plus 1. So we have to include and exclude. So the -1 to a power is becoming +1 and -1, +1 and -1. So this is another way to write this. This is S1 minus S2 plus S3, etc., minus S4 plus -1 to the n minus 1 times Sn, where we've defined S1 to be probability sum of all of the individual events. S2 is the sum of all the pairs for all this distinct I and J. And in general, SK is the sum over all distinct choices of K subsets. How do we prove this? Okay. It's a little bit of a tricky proof depending on your level of comfort with proofs. This is going to use induction. Induction on n. We've already proven this in the case of, well, if there's only one event, it's trivial. It's just probability of A equals probability of A. So how does induction work? You need to establish a base case. And for us, the base case is going to be n equals 2. Okay. And we can show that the formula we've given above, the general formula, is just exactly the base case in the case that n is equal to 2. And now what we do is we assume, and the induction step, is that we assume it's true for the value n, and then we leverage the base case and the assumption that it's true all the way up to n to prove that it's true for n plus 1. How do we do that? Okay, well, for n plus 1, we're looking at the probability of the union from I equals 1 to n plus 1 of AI, which can be expressed as probability of an plus 1 union with the union I equals 1 to n of AI. Okay. Now, this is the probability of a union of two events, so we can just use the base case. So this is probability of an plus 1 plus probability of the union I equals 1 to n of AI minus the intersection probability of an plus 1 intersect the union. Okay. Now, an plus 1, that's just an plus 1. What's this? This is the induction step. So that's actually the thing we're trying to prove. So we can take that for granted because we've assumed that to be true by the induction step. Okay. So this is sum over all subsets of n of -1 to the size of j plus 1. Another way to write this. Fine. Size of j plus 1 has the probability of I in j of intersect I in j of probability of intersect I and j of AI. And then the probability finally minus the probability of, another way to write this is as the union of, you can distribute the an plus 1 into the union. So it's union I equals 1 to n of AI intersect an plus 1. All right. Now, what do we make of this? Here's what we make of it. We're going to look at we're going to now fold this first term into a different term. So we're going to now break this up as, okay, the sum, this term, and then we're going to have, let's call it a green term. Okay, so the first term, the pink term, is actually going to be rewritten as the sum of all subsets of n plus 1, not of n, such that n plus 1 is not an element of j. Well, if n plus 1 is not an element of j, then this is not, this can just be regarded as a subset of n. So it's exactly the same as this initial term. It doesn't change at all. And so this is actually identical to this. And then what we're going to do here is we realize, okay, what's going on down here is we have inclusion-exclusion again. So, all right, wait, let's write it a little. This is going to be inclusion-exclusion of n sets, but each one of those sets is intersected with n plus 1. So it's minus n minus 1 to the j plus 1 probability of an plus 1 of intersection I and j of ai intersect an plus 1. And this now includes this first term up here, because the empty set is a subset of J. When I is the empty set, we define the intersection of I in the empty set of AI as just omega. And so it's just an plus 1. So now another way to write this, though, is to realize, well, this can be written as an plus 1 intersect the intersection I and j. And so now what we're left with is same first term, j a subset of n plus 1 that does not include n plus 1. So that's exactly the same. Plus, another way to write this second term, this green term, is that these are subsets of n plus 1 that do include n plus 1. Ah, okay. So, sorry, this should have been a minus here, though. And so now that they include an extra term, so they include the extra element, and so we can get rid of the minus by folding it into the extra element and putting it here. And now an plus 1 will be in every one of these, and we have this again. So this is the same. Okay. And now we realize that the set of all subsets in n plus 1 is equal to the set of all subsets that do not contain a given element union the set of all subsets that do contain a given element, and that this is disjoint. So in other words, this here simplifies to sum over all subsets minus 1 to the power size of j plus 1 probability of the intersection of the subsets indexed by j, and we've recovered inclusion-exclusion. Another way to write this is just to, nothing wrong with how I wrote it, but it's actually just better to write it as sum over all subsets of n minus 1 to the number j plus 1 times the probability. And now these are exactly identical. So this is the same as this. And we've proven That's inclusion-exclusion. Okay, so that's actually a little bit of a tricky proof if you haven't seen this stuff before, if you haven't worked through this stuff before. So definitely encouraged to look over that, study that again. If you didn't get it the first time, and I wouldn't expect that you did if this is the first time you're seeing that, or even if it's not the first time you're seeing it. Okay, let's do another one. The probability of exactly m little m out of little n events. Okay. All right, so let's define events. A1 up through AN. And for each little m, from 0 up to n, let's let E sub m be the event that exactly little m of the AIs occur. Then the probability of EM is equal to sum from j equals 0 to n minus m see. J equals 0 to n minus m of -1 to the j m plus j to the j to the m, I'm sorry, m plus j to the m s m plus j, where we define S0 to be equal to 1 by definition. And the S's are defined up above. In general, S sub k is defined as the sum of subset ik of the probability of the intersection of age. Okay, so this is a pretty tricky one. How are we going to do it? Well, we're going to do it again by induction. Okay. How are we going to do it? So we do it by induction. So let's start. First is to see that this is true for m equals 0. Why? probability of E0. This is the probability that exactly 0 of the events occur. Right? 0 of the events occur if the union does not occur. Probability that the union does not occur is 1 minus the probability that the union does occur. Sometimes I won't label these unions very carefully. And that's because it shouldn't confuse, but I will try to be careful there. And the probability of the union, well, this is exactly what we've already seen. This is inclusion-exclusion. So this is I equals 1 to n minus 1 to the, let's say, inclusion-exclusion, which we expressed here, it's minus 1 to the j plus 1, right? So it's I equals 1 to the n minus I to the I plus 1 of SI. Okay. And now in this case, m is 0, so it's sum from, this is saying, right? According to this is the sum from, so let's make this clear. Star, call this double star. Double star in this case is sum from j equals 0 to n minus 1 to the j m plus j, choose m, j choose 0, s m plus j. Again, m is 0, sj. Okay. So this is the sum j equals 0 to n minus 1 to the j s sub j. So I have an s sub I plus 1. S0 is defined as 1. S0 is defined as 1. Right? And that's going to be taken care of by this. And then the others are minus 1 to the power j. I have an extra minus sign out front here, which I can absorb into this minus 1, which I can either absorb by multiplying, so it would be I plus 2, but knowing that minus 1 goes minus 1 plus 1 minus 1 plus 1, right? So what happens, I can actually drop it down as well. So this is the same. Okay. Another way to write this would be drop this down and add 1. And now we can add the 0 index because s sub 0 is defined to be 1 and minus 1 to the 0 is 1. And we're done. Good. So we've proven the base case. So now let's assume that m is bigger than or equal to 1. For any subset I, capital I, we're going to define A sub capital I as the intersection over all indices in I of AI. Okay. And we define A sub empty set as omega. Okay. And now what we're going to do is we're going to let script I sub m be the set of all subsets of n that are size m. Okay. So now for I, an element of script I sub m. So for any index set that has m elements, probability of AI intersect the intersection of J not in I, AJ complement. So this is the event that everything in I happens and nothing outside of I happens, right? Everything indexed by I happens, nothing not indexed by I happens, okay? Or everything not indexed by I doesn't happen. So this is by inclusion-exclusion, probably AI minus probability of AI intersect the union of J naught and I of AJ. Right? Why? Because this is intersect Y. I'm going to do a little work up here. Intersect AJ complement is equal to the complement of the union of the AJs. And so that means that AI intersect AJ complement is equal to AI intersect the union of AJ, that whole thing complement. This equals AI minus AI intersect. All right, we're running out of space here. Move this too. Union agent. Okay. That's why that works out by the rule of differences. Okay. We can use distributive law. It's the probability of AI minus probability. You can bring the union out. And you can just have AI. This is just the distributive law of the set theoretic operations. And now what you realize is, okay, this here is governed by inclusion-exclusion. Okay. So we can actually write this pretty nicely as the sum from k equals 0 to n minus m, right? N minus m, we'll see why in a second, minus 1 to the k, the sum over all subsets of I complement such that the size of J is equal to k of the probability of AI intersect AJ. This is by inclusion-exclusion. So this is an application of inclusion-exclusion, right? The case where k equals 0, means that J is the empty set, so this would just be nothing, and we would have this left over. So that's where the first term comes from. That's where this first term goes. And then the rest plays out as usual, just using the usual inclusion-exclusion formula. Okay. So now, because A sub I intersection of J and I of AJ complement, these are all disjoint. And they all have a union of E sub n, right? Because I'm picking exactly M, and I tells me exactly which M are occurring, the index set. Then what does finite additivity imply? Well, it implies that probability of EM is, by finite additivity, I'm summing over all of these index sets because they give me disjoint events of the probability that we calculated up here for any given disjoint event. This probability here. Right? So this is K equals 0, N minus M, minus 1 to the K, sum J subset of I complement such that J is of size K, probability of AI intersect AJ. Okay. Rearrange the order. So we're summing the finitely many things. So we can actually add them up in whatever order we want. So I'm going to rearrange this. Just rewriting. But now what do we have? We have sum K equals 0 to N minus M, minus 1 to the K. And now we're summing over all size M index sets. We're summing over all subsets of J, subsets of the complementary index set of a given size. This is the same as saying, okay, let's pick M indices from M plus K. Let's then pick a subset of size M plus K. And let's take that probability. And that's what SMJ precisely is. SM plus J precisely is. So this is SM plus J. which is star, double star. Whew. All right, well, that was definitely pretty involved. So a lot of notation there. Throwing a lot at you at once, pretty much using all the concepts that we've learned so far, and that's why we did this example. Worth going over a few more times to make sure you're comfortable with that. And let's stop this here, and we're going to come back with an application of this in the what's the so-called matching problem to wrap up this chapter.